Yeah, so thank you very much for the invitation to talk to you today. I will, as Sanjay said, I will talk about direct dark matter detection and also then later a bit about indirect dark matter detection. And I've been loosely following this workshop in the past few days, and there's been a lot of talk. So thanks for still being here. And it's getting late in the afternoon in India, and I'm sure you're having very busy days. So with a lot of information to digest. So I hope I can keep you interested on this one. Yeah, so more generally, I saw yesterday there was already a talk on direct dark matter detection by Laura Baudis, which I guess should have given you a bit of an overview of the field. And I guess what I'm doing today is to dig a bit deeper, to go a bit more into the details, but maybe explain a little bit more how these searches work, how different measurements are done, and to talk a bit more about the different experimental approaches. So apologies if the introduction, if you've already heard this, but I hope it's useful to set the scene. So the starting point, right, is, well, how much dark matter is there? How is it distributed? And then how can dark matter interact? And I guess the general answer to that question is, well, it can interact either with nuclei or with electrons. And then again, depending on the nature of dark matter, is how large are these signals and how can we detect them? So, and here I just have a sort of an incomplete list of, let's say, the most popular ways of going about looking for dark matter interactions in some detectors. And so the first one I'm going to talk about is the noble liquid detectors. And this includes both liquid xenon and liquid argon. And so the main experiments here are LZ and xenon n-ton. They will produce results in the coming years. Panda X photon just released the result a few weeks ago. And then with liquid argon, you have DarkSide 20K as the next big project. I think, well, I will spend quite some time explaining how these experiments work. And I guess, given the title of this conference, so looking for SUSY means we're looking for WIMPs at the GeV scale. So this is probably the most relevant technology in that sense. Then they're all, yeah, is there a question? No, okay. Then there are also solid state cryogenic detectors. So these are based mainly on germanium or silicon crystals, and examples for such experiments are CREST, Edelweiss, CDMS in its different incarnations. Other detection techniques include superheated liquids, so bubble chambers. And then there are also, let's say, the room temperature ionization detector. So this is sort of a more recent development. And then the early searches, they used room temperature scintillators, but I won't go too much in that. And yes, there's many more, and there just isn't enough time to discuss all of these in just one lecture. Okay, so let's move on. So what do we know about dark matter in our galaxy or in our environment? And so we have measured the rotation curve of the Milky Way, which is shown here. And what one then does, one uses the standard halo model to get the velocity distribution of dark matter. And So what happens is that the dark matter halo, or we exist in a dark matter halo, at least that's what we think it is, and the luminous matter in our galaxy exists in a disk that is rotating at around 200 kilometers per second. One thing to note is the halo here is not to scale. It's about 10 times the size of the Milky Way. And so people have determined the local dark matter velocity distribution, which is shown here. And so there is the standard halo model that gives you this value of around 220 kilometers per second. I should say there are new measurements from Gaia that slightly disagree, may point at slightly lower values, and that there's other data that may point at slightly higher values. So I think this is just one thing one needs to bear in mind, that are the assumptions that go into when we later set limits on dark matter cross sections, that things like this, you know, the results will depend on these assumptions that one makes for the velocity distribution. And then, so as on Earth, we travel with our sun in a spiral arm of the galaxy. So what we will see is basically this dark matter wind blowing at us with around 200 kilometers per second. And the Earth itself is going with around 30 kilometers per second around the sun. And so depending on the season of the year, we are going either with or against this dark matter wind. And as such, in some experiments, we should even be able to see a modulation of the dark matter flux once we are able to detect dark matter. Okay. So how do we go about searching for dark matter? I'm sure you've seen this diagram many, many times. There are different ways. And I will talk about the two at the top here. So one is scattering, which is what we call direct detection. So a dark matter particle interacts with our standard model matter, but it just scatters off and transfers some energy and momentum. And another way, which is going to be the second part of my talk, is annihilation. And this is what we call indirect detection. And I believe you've already had talks about dark matter production at colliders, and presumably mostly in the context of supersymmetry. So what could dark matter be? So there's quite a variety of proposed dark matter candidates, and the most prominent probably is still the WIMP, the weakly interacting massive particles. But WIMPs are by far not the only proposed dark matter candidates that are around. So another popular option would be axions or axion-like particles. Then there are extensions to the standard model that predict the whole rich dark sector where dark photons could play the role of dark matter. Other suggestions are sterile neutrino, and there are many, many more. And as you can see on this sketch at the bottom, these possible candidates for dark matter, they really span many, many orders of magnitude, both in mass and in interaction strength, that at the end of the day would give you the correct relic dark matter density that we have measured from the Planck data. So one thing to note is that the standard thermal WIMP here is really just covers just a small mass range of what could be possible. And obviously, if the mass varies over so many orders of magnitude, the way how we can detect such interactions changes considerably, because the momentum transfer that is possible from such a dark matter particle to a standard model particle changes in just the same way. Okay, so I'm actually, even though you see this, this entire dark matter zoo, I'm mainly going to talk, or only going to talk about WIMPs today. So I hope that doesn't disappoint you, but it's what you get in SUSY, and I think that's what most of this meeting is about. And I imagine you have heard this many times. So the nice feature about WIMPs is that if you have a particle at the electroweak scale, so order of 100 GeV mass, and if it has interaction strength that is similar to that of the weak force, you get the right observed relic dark matter density. And well, you may think this is quite a good argument, because we know that other particles at the electroweak scale with such interaction strength exist. So why shouldn't there be another one that we just haven't found so far? And based on this, so again, based on the dark matter density, so how much dark matter is there? So this is something that's nice to keep in mind. So the dark matter density is 0.3 GeV per centimeter cubed. And if you then assume a dark matter particle has a mass of 100 GeV, then basically we end up with one dark matter particle in every can of thumbs up. So remember that next time you drink one of those, you may have swallowed a dark matter particle. Okay, more seriously now, let's move on to the techniques about that I used for direct detection. And so what we need is, we need a finite probability for this dark matter to scatter with our standard model particles. So one thing to consider is that all the evidence we have for dark matter is basically from astrophysical or cosmological observables, and this is all based on gravity. And if dark matter really just interacts via gravity, we will not have a chance to see it in any detector that we built here, because the interaction strength would just be too small, and we could not hope to see any such interactions. So we are hoping that it also interacts via some other force, and we can observe such scattering. And so in particular, we are searching for interactions with either nuclei, so where we then can observe a nuclear recoil, or interactions with electrons, which are electron recoils. And in order to become sensitive to this, because we know dark matter is only very, very weakly interacting, typically the larger a detector you can build, the better. And at the same time, however, you need to be able to suppress all other background that can give you similar signals. Yeah? Okay, so what happens if we have an interaction between a dark matter candidate or dark matter particle and a nucleus? Well, a nucleus or an electron, we can have both. So in the materials that we will consider, the signals we can now get out is scintillation. So there's a photon emission, for example, from if we talk about xenon, if you have an interaction, you'll typically get the xenon nucleus into an excited state, and it then will emit a photon when it falls back to the ground state. And this is in the ultraviolet, but we can detect these photons. Another thing, if the momentum transfer is large enough, is the nucleus will recoil by some amount, and this can give you ionization in your medium. So you get free electrons that you can detect, for example, as a current. And then a lot of the energy will go into temperature, and again, depending on your medium of detection. So, for example, if you have a crystal, you can register them as phonons. So these are the ways we can see these signals. And I think the next slide you saw already yesterday from Laura, which gives you an oversight of past and future experiments or current experiments taking advantage of these different signals. And so the modern experiments, they are usually taking advantage of at least, of two of these signals. So these are the experiments that are sitting here in between. Yeah. So, for example, if we talk about the liquid xenon or liquid argon experiments, in these experiments you get both light emitted, so scintillation light, and you also get ionization, so you get a charge created. Then for the cryogenic solid state experiments, so for example, super-CDMS Edelweiss, you get this heat, so you can detect the phonons in the crystals, and you get ionization. And then here CREST, for example, has a different approach where you get also the phonons, and in addition you get scintillation light. Okay, and then there are lots of other experiments that are just making use of one of these three possible signals. But the advantage really is of combining two of them is background suppression. So it gives you a much better control over other processes that are happening in your detector that do not stem from dark matter interactions, and that you can suppress that way. Okay, so if you're interested in this field, there is this report here, which really is a nice summary of all the direct detection methods. And this schematic basically just summarizes what I just mentioned on the earlier slides. So from these crystal targets, one can get scintillation light. Then one can also combine them with one has other crystal targets where you get a charge and then a heat signal, so where you can detect phonons. Then there are the liquid xenon and liquid argon detectors, and there are two approaches. One is just with a liquid target, and then the more modern ones have a dual phase, so where you have a liquid and a gaseous phase. And I will talk about how that works in quite some detail. There are bubble chambers where you see a signal of an interaction as bubbles emerging, and they, because of the target materials one can use there, they are quite sensitive to spin-dependent scattering of protons. And then this is something that's a little bit more to the future, will be directional detectors. Okay, so let's maybe take one step back again, and let's think about again what is happening with this energy transfer. that we can get from a dark matter nucleus interaction. And what we can see here is that what you see here is the expected rate. So how many interactions you expect for a given cross section here, and a given mass of a WIMP, and then as a function of the threshold recoil energy. So what you can see is that, first of all, this depends on your target, so what medium you use from which you are scattering. So the examples here shown are xenon, germanium, and argon. And the figure on the right shows you the same, but then for 100 GeV dark matter particle instead of 50, this will have a different cross section. And well, one thing to note here is that the rate here now is on a log scale, and furthermore, it has changed from counts per ton per year to counts per kilograms per year. So the signals that you get out are of order, so the recoil energies are of order tens of kilo electron volts. But you see the rate that you can observe drops off fairly quickly. And so the further down you can go in threshold, the more, the better is your chance of observing a dark matter interaction, because you include more of the spectrum. Now, these rates, they increase with a squared, so that's why it is good to have heavy target nuclei like xenon here. But unfortunately, not everything is rosy, because at high energies, this is then suppressed because of form factor suppression. So it's different target materials. They all have the advantages and disadvantages, and I think that's also why there's a wide variety of experiments that really tries to probe all of this. And another comment that to make here is that the shape of these distributions, it depends on what you assume for the velocity distribution of the dark matter. So this is what I touched on earlier. So all these things depend on the assumptions you make. And so for these curves here, again, the standard halo model was used. Okay, and then obviously the more recoil you get, the larger the recoil, the higher the ionization, the larger the signal that you can detect in your detector. So let's talk a little bit about these two-phase xenon TPCs. So TPC is a time protection chamber. That basically means you have a strong electric field across your detector volume. And then if you have some ionization, you can strip out these electrons and measure them. But what happens in particular in this type of detector, so what we are looking for is an incoming particle. It will scatter off a xenon nucleus inside the liquid volume, and it will disappear again. If it is dark matter, the chance for interacting is so small that you will only get one in your detector volume. And what then happens is, as I mentioned, the xenon nucleus gets excited, and it will emit what we call S1, an S1 signal. So there will be some photons emitted, but the number of them is fairly small. So this is like order 10 photons or something like that. And this is a prompt signal. And basically, this tank of liquid xenon is instrumented with photomultiplier tubes, both at the top and at the bottom, and we can see this faint light signal. What also happens is the xenon nucleus recoils, and this will lead to some ionization. So we'll get a number of free electrons in the liquid xenon, and as we have a strong electric field applied across here, they will start drifting through the liquid xenon towards the top, and then near the top we have the second phase. So we have a gaseous phase on top of a liquid phase, and so as the electrons get stripped out from the liquid into the gaseous phase, again they will create light, and in this case this is much larger. So here we are talking about thousands, so order of 1,000 photons per electron. So in this case we really get a strong light signal, which again we can collect with our photomultiplier tubes here. And so this is the characteristic dark matter signal in one of these detectors. A small light flash from this S1 signal, from the scintillation, followed by a large light flash from the ionization. And this large ionization signal is delayed because the electrons need to drift through the xenon and then reach the top, whereas the scintillation light is prompt and basically travels directly, right? Okay, now, and this nice signature is really useful in suppressing backgrounds, because this is what we expect from a dark matter interaction, or from a nuclear interaction, if you want, a nuclear recoil. This also helps us because we can measure the time at which these signals arrive. So this helps us to get an estimate for where in the detector this interaction occurred. Because you know the drift time of the electrons, the drift velocity, so the delay between the S1 and the S2 signal can tell you how far down the interaction occurred. And in the horizontal, in the XY plane, we can tell from the light pattern that appears on the PMTs at which position this interaction occurred. And I will talk about this shortly, but background contributions, so non-standard model particles that might enter your detector from the outside, they typically would interact very soon after entering the xenon. They normally can't penetrate very deep into the xenon. And so this position reconstruction again is an indicator, you know, if you have a signal that comes from the center of your detector, this has a much higher probability to be a dark matter signal than to be a background event. Okay, so talking about backgrounds. So most of these searches is really about understanding your backgrounds and suppressing them as good as you can. So, excuse me. So here's a schematic of LZ, but Xenon, Anton, for example, or Panda, they are all fairly similar. So you have this liquid xenon time projection chamber in the middle, which is instrumented with this photomultiplier tubes at the top and the bottom. And then you have different layers of shielding. So in LZ, there is what is called the liquid xenon skin. So this is just an extra layer of liquid xenon that is around the TPC. which acts as a shield. Then this is again the cryostat is surrounded by a tank of gadolinium doped liquid scintillator, which itself is sitting in a passive water shield. And again, this outer detector then is instrumented with photomultiplier tubes, so you can detect any interactions that happen in the outside here. And then just to be extra safe, you put the whole thing about 1.6 kilometers underground into a mine to suppress cosmic backgrounds. Okay, so this is the setup. Let's dive a little more into backgrounds and sensitivities. So what kinds of backgrounds can we get? What is it that we have to mitigate? So there are, first of all, there are external sources. So as I mentioned, cosmogenics, that, you know, you put this underground, the rate is much reduced, but it's not zero. You can get radiation from the experiment cavern, so you can have gamma emission from the rocks. And in fact, different laboratories around the world have different background radiation environments. There could be other new physics, for example, neutrinos. I'll touch briefly on that later. And then you have all these internal sources. So most, well, one of the things you need to consider is radioactive materials in your detector components. Emanation of radon from your detector components. So radons is your enemy. There is radioactive dust on surfaces that can all give you backgrounds. And then there are simply contaminants in the xenon, so impurities in the xenon. And when you start looking at this, you get a picture like this. So the top here shows you background contributions from electronic recoils, and at the bottom from nuclear recoils. And so here on the left, you see these are solar neutrinos, give you a large contribution at very low recoil energies. And then you have atmospheric background, and then here you have these materials background, which is sort of relatively flat as you go out to rather high nuclear recoil energies. Remember, if you remember the figure I showed earlier, so for a WIMP of 50 to 100 GeV, that spectrum really ends at around 40 keV. So most of the WIMP signal is sort of in this lower range. And again, so electron recoils you can get from radon, different radon isotopes, kryptons, and again your materials, and again notice the energy range here goes out up to 200. So really the sort of the left part here is the relevant part for a WIMP search. So our backgrounds are mainly gammas and neutrons, but also some neutrinos. Then there is intrinsic radioactivity in the liquid xenon. So there are beta decays of some lead isotopes and krypton 85. And before you start your experiment, there is a big campaign to remove any krypton from your xenon. And this goes down to 1 krypton atom per 100 trillion xenon atoms. Neutrinos can give you background by scattering of atomic electrons, or you can get the neutrino coherent nuclear scattering. And yeah, for all these reasons, we have our veto detectors, because in order but at least for the internal sources, to get into the liquid xenon, they have to pass our outer detector, the skin detector. And what would happen is that they normally, they scatter multiple times. And so you can time correlate the signals you see in your veto detectors with a possible signal inside the detector. And that way you can reject such backgrounds from neutrons or gammas. So here's a sort of a sketch, you know, a neutron that would bounce around the tank and would give you repeated signals. And based on that, you could reject that because the dark matter would really just give you one interaction and one interaction only. And the effect of this we can see on this slide here. So at the bottom here we see the color scale gives you the counts per ton per year. So the number of events we would expect to see. And this here is basically your detector volume. This is the radius of your liquid xenon TPC. This is the height here. And so one can see without the veto, you get quite a lot of interactions, in particular, you know, near the surface of your xenon. So most of these background interactions or sources, they cannot penetrate much into the xenon without interacting, which is quite nice. So again, mentioning the position reconstruction. So should we observe events that come from the center of the detector, it is much more likely to be a signal than a background event. And on the right, you can see once you start including this veto, by how much you can reduce these backgrounds. And on top of that, then what you do is you do a fiducialization of your detector. So for your analysis at the end, you will just use a subset of the volume of your entire detector in which you conduct your WIMP search. Sorry, I've seen there's some comments in the chat. Okay, how do we identify the source of the background? And so different backgrounds, they will give you different types of signals, and mostly it will be electron scattering. The nuclear scattering is really quite difficult, but as you will see in just a moment, we don't expect many of these because of all these vetoes and shielding that we have in place. And so what you have, right, what we see are signals in our PMTs, and you can different types of interactions will give you different types of number of photons, basically. Possibly the time distribution will also be different, so the waveform itself, and you can use all this to identify different types of background. Neutrino coherent scattering, again, I'm going to touch on this slightly later. We will, it's going to be quite rare, but over the lifetime of LZ, it is expected that we observe it. But I will touch on this in a few minutes.
Sure, we'll wait.
Okay, so so this was basically the detector setup. Then we have the internal backgrounds, and so there are, when you build this detector, every single material, every single screw, it's considered what it is made of. That it all gets assayed for its purity and how much it radiates. Then for radon emanation, there's been, radon removal systems have been put in place. Then everything is done in ultra clean rooms to be dust free. And then you have this this xenon purification to remove contaminants. And once you've done all this, this is what you expect over the lifetime of the experiment. And so here are the background sources, and they're distinguished into electron recoils and nuclear recoils. And you see that most of this comes from electron recoils. So there is the detector components. You expect nine events, surface contamination 40, xenon contamination is the largest contribution with around 800, and you're sort of limited what you can do there. The lab and cosmogenics is relatively small again, and then you just you have some other physics backgrounds. And what you can see here, that the nuclear recoil counts, they only go, we really only expect one interaction there from background processes. And then you have your right, you do your analysis. We'll talk about this on the next slide, but the assumption is that about 99.5% of the electron recoils you can reject, and for nuclear recoils it is much more difficult. You only have a rejection efficiency of 50%. Okay, so the analysis itself then is done mostly in these two variables. So remember, I talked about that the typical dark matter signal is this small light flash. This is one light followed by a large light flash. And what you see on this plot here is you have these two quantities plotted against each other. So on the horizontal axis, you have this S1 light, and C stands for calibrated. So and it is in units of photons detected. And then on the vertical axis, you have the large light flash, and you see this is on a log scale. So here we have thousands to 10,000s of photons, whereas in the S1 signal we really have order 10 photons. And different processes, they show up in different regions of this distribution. Yeah. So in blue here you see the electron recoil band, then somewhat below, but still separated. And I think these bands, they include 90% of the events. You see the nuclear recoil band, which is slightly lower. And then here for illustration, is a 40 GeV WIMP signal is overlaid where you would expect it. So basically, this plane, it helps you to identify, to distinguish different types of interactions, and then hopefully later on also to identify, say something about, what kind of mass your, if you see a dark matter signal, what kind of mass it has. But basically, depending on where a signal would show up in this plane, you could tell something about the mass of the dark matter candidate. And then here, this is the coherent neutrino scattering. So these are neutrinos from the sun, and we expect them to show up here on the very bottom left corner of this plot. And so this is just to say, this is a simulation that corresponds to the full exposure that LZ expects. So this is 1,000 live days, which will happen over a period of something like 5 years, and with a target of 5.6 tons of liquid xenon. So, and then coming back to this question just earlier about how do you distinguish different interactions. So one thing we also do is you do a quite intensive calibration campaign. So you put gamma sources, beta sources, alpha sources, or neutron sources rather in your detector, and you record the response of your detector to these. And for certain for these sources, for some of them, there's only one transition. Exactly the energy of the electron or of the gamma that was emitted, and you can see where this shows up here in your in this plot, and that allows you to calibrate your detector, and so and also you see that different types of sources, so different energies and different types of interactions, they show up in different regions of this plane, and that allows you to distinguish then these different processes. Does that make sense? Or did that answer the questions?
Yeah, thank you. You answered me.
Okay, great. Yeah, so based on so this then goes into a profile likelihood, and you have to do some fancy statistics, but at the end you come out with a limit. And again, here this is the projected sensitivity for LZ compared with the current limits from xenon 1 ton and Panda 4 ton, which just came out, I think, last month. And so you can see that what we expect to reach in the next 5 years or so is sort of a factor 50 improvement, if I got it right, in the cross section. So it's quite something. And you see this yesterday. I know there was a bit of discussion about this neutrino fog. So this is once you start becoming sensitive to, you will start to see interactions with neutrinos, and here in this range we are still quite some distance away, but here where we have the solar neutrinos here at we are expecting to see some of these interactions, and maybe this is clearer on the next plot. So where you see here, there is a line where we expect one neutrino event, and you see that in this region, the projected limit from LZ, which is the black line here, crosses this how should I say, the area or the region from where we expect neutrinos to show up. Yeah. So I noticed there was some discussion yesterday about how this works, but that the neutrino cross section is fixed, right? But as the sensitivity of your experiment grows, you just start seeing more and more of these interactions. So as we cross this expected, line here for neutrino interactions, we expect with the full exposure some of these to show up here. Then the other thing that this plot shows is sort of rather than just setting limits, which is much less exciting than having a discovery, there are the 3 and 5 sigma sort of discovery reaches, and obviously they are weaker than the 90% confidence level limit that is usually set here, and but they are still below the current best limits. So there is a region of parameter space where we could, if we're lucky, we may have a discovery. Okay, so far we've only looked at spin-independent scattering, but we can also have spin-dependent interactions. And in this case, the WIMP is assumed to be a fermion that is coupling to an unpaired nucleon spin. And so for these interactions, it really depends on your detector material. So if you have a nucleus with unpaired spins, then they are blind to spin-dependent scattering. You just cannot do that measurement there. But if you have nuclei with unpaired spins, such as fluoride or germaniums and these xenon isotopes, you can be sensitive to spin-dependent WIMP scattering. And neutrons and protons typically contribute differently to the total spin of the target. And so these spin-dependent results, they're usually split in either WIMP couplings only to neutrons or only to protons. And one experiment that is rather sensitive to this here is are these bubble chambers that I mentioned earlier, and mainly this is because they use these refrigerants that include quite a lot of fluor, and this really enhances the sensitivity to spin-dependent scattering, because you have this unpaired proton in your target. And so the way this works is you keep these superheated liquids just below their boiling point, and then if you get even a small energy deposition at some place in your detector, it will lead to a local phase transition of the superheated liquid, and a bubble will form. And here are just two screenshots where you can see there is, on the left here, there's a small bubble forming here, which is then rising and getting bigger. And so that way, again, yeah, you know, some interaction has happened. And as I said, because of the target material, this is very sensitive to spin-dependent scattering of protons. And there are results from PICO, and an upgrade with PICO 500 is forthcoming. So here are these results, just for comparison. So you have the, I should say, so for xenon is also a good target material in this case, because these isotopes, xenon 129 and 131, which have unpaired neutrons, they have quite large abundancy, right? So if you add these together, about 50% of your xenon is from these isotopes. So it gives you a good sensitivity to WIMP neutron scattering, which is shown on the left here. And then on the right, you have the WIMP proton scattering. And here you can see the already existing limit from PICO is much stronger than that of these liquid xenon detectors. Okay, I think it might be good to break here for either questions or just a general break.
Sure.
Because
is there any question from the first part? Can you raise hands or type? I see no hands. So Henning, just wanted to ask you a quick question about this projection for 5 years. Is it just a statistical projection, or the background, the improvement of understanding background is taken care of?
You mean these limits?
Yeah,
yeah, they include systematics. Yes, yeah. These are like
the improved detector effect and understanding. They're all part of it.
Yes, yeah.
I see. Okay, so we'll take about it's 5 minutes break. Is it, Henning? Is it okay?
Yeah, 5 minutes is good.
Yeah, 5 minutes to grab coffee and then come back or something. Yeah.
Okay, great.
Okay, I will see you in 5 minutes. Yeah.
Okay, shall we continue or have some other questions come up in the meantime that people would like to ask?
Unless others have the objection, I think you should continue probably. Sanjay is muted.
Okay.
Please go ahead. Please go ahead.
Okay, so, right, what I covered, well, I mainly spoke about LZ because that's the experiment I'm involved in, but as I said, Xenon, Enton, or Panda X, they all work in the same or very similar ways. And they are probably the most relevant for, for WIMPs that are in the 10 to 10 GeV to TeV range, because they give you the best sensitivity there. So what I'm going to talk now is cryogenic solid state detectors, and they work differently, as I mentioned in the introduction, and they have sensitivity. Better sensitivity at light for light to dark matter, so below 10 GeV, let's say. And so here the state of the art again is to make use of two of the possible signals that you can detect, and in this case you have phonons, and then in addition you measure either ionization or scintillation. And typically these crystals, are the target here is silicon or germanium, which are lighter nuclei, and so they're also better suited to detect signals from smaller from lighter dark matter. Yeah. So basically the reason the liquid xenon or experiments loses sensitivity for lighter dark matter masses is because you just don't have a large enough momentum transfer from a relatively light WIMP to a heavy xenon nucleus, and you just cannot record that. Okay, so let's talk a little bit about super CDMS. So as I said, they use silicon and germanium crystals to detect dark matter. What they do is they cool them down to very low temperatures. Yeah, so it's 15 millikelvin, and this is in order to reduce thermal noise. Yeah, so that basically you just have a crystal sitting there perfectly quiet, and if something comes in and hits the nucleus, you get a lattice vibration, and you can detect those phonons, and in addition you get ionization, and you can read out that charge. And because of they're trying to measure this heat and the phonons, these detectors are then also there's also vibration isolation, so that they sit there perfectly still. What is a problem is to grow these crystals large enough so that you get large target size, and when they get big, then, well, you need to have them very pure, and you want to extract a charge, and so the way out is, rather than having one big detector, is having lots of small detectors. So you build these many identical devices that you then put in the same cryostat and cool down. And in this case, the energy threshold here is around 70 electron volts. So if you remember when I talked about the liquid xenon detectors, we were talking sort of several kilo electron volts, right? So the sensitivity here is very different. They can pick up much smaller signals. Another example is this CREST, which, rather than trying to measure an ionization signal, they have this particular scintillating crystal, so that will emit scintillation light as well as give you the heat signal via phonons. The detector mass here is very small, yeah. So this has 24 grams. If you compare that to the 5.6 tons of liquid xenon, it is tiny, right? But again, you gain sensitivity because you have a very low energy threshold. So here it is down to 30 electron volts, so very small. And what we then see here is that results in the so the sensitivity to low mass WIMPs. Here you can see that we have these exclusions here from the liquid xenon experiments here, which then lose sensitivity as you go to smaller WIMP masses, as I said, because you no longer get a sufficient recoil that you can register. But then here you have these experiments like CREST, Edelweiss, CDMS coming in, which become more sensitive for the small WIMP masses, but it's still at much larger cross sections, yeah. And one big reason for that is also just the size of the targets that one can produce. But looking forward, the future is bright here. Yeah, again, you see projected sensitivities for super CDMS, CREST, Edelweiss here, and note the change of scale in these plots. Yeah, so the scale on the plot on the right here stops at 10 to the minus 39. So we are really, if you put this on the same plot on the left, we are exploring. We are exploring these regions down here. Yeah, okay. And one thing I wanted to mention as well, because I listened to the discussion yesterday a little bit about the neutrino fog. And when you start seeing neutrinos, slightly depends on your target material as well, right? Because it depends on your neutrino target material cross-section. And that is slightly different for different types of targets. So that is illustrated here in the figure on the right. So this here is still for spin-independent dark matter nucleon cross-sections, but we can also then look at dark matter scattering of electrons. And one recent experiment here is this Sensei, which is a CCD. And basically, what happens is you have a dark matter interaction with an electron in the valence band, and it just transfers sufficient energy to put it in the conduction band. And so the silicon band gap is 1.2 electron volts. So, you know, you become sensitive to even lower energy transfers, and therefore to even smaller dark matter masses. And on the right here is a sort of an example picture where different types of processes they leave different types of signals in your in this camera, basically, right? The CCD is sort of what you have within your mobile phone camera as well. And these tiny dots that you can see, these are these one electron events. And they have set limits as well, quite strong here. Now this is a cross-section for scattering of electrons, so no longer of nuclei. And what you can see here, that the scale here now, that the top end of the scale here is 1 GeV, and they are probing MeV dark matter. The other experiments that I mentioned earlier, so the cryogenic detectors and also the liquid xenon, liquid argon, they have some sensitivity there using, you know, they're also using electron scattering. The thresholds, depending on the process, the thresholds can be lower there as well, but nowhere near as the thresholds in these dedicated experiments. But you gain from a much larger much larger target mass. And then as we move on to probe lighter and lighter dark matter, we go to smaller and smaller signals. And so we go from noble liquids to these semiconductors and scintillators to superconductors eventually. And I just wanted to show this here. There's sort of a prototype that is using single photon superconducting nanowires. And the idea here is that the photon or the dark matter interacts with electrons in a Cooper pair, and it breaks the Cooper pair. And that basically, all of a sudden you have a small resistance that you can measure. These are very small signals, so 1 millivolt pulse for 10 nanoseconds. And the detector here, the demonstrator, the active material here is 4.3 nanograms. So it's really tiny, but they run it for some time with an exposure of order 10 to the minus 5 gram seconds. So, oops. So really very, very small, but you do have some sensitivity here. It's the black line here that shows exclusions for light and heavy mediators on the left and the right. And again, here the scale now is from 100 MeV down to 10 keV dark matter mass. So you can probe much, much smaller dark matter masses here. They also give some projections, but I think one really needs to be careful with them because the largest projections here, they talk about exposures of gram years or kilogram years, whereas what has, before you have a kilogram of nanowires, I think it will take a long time, from the current demonstrator that has nanograms and has been run not for years, but just for a few days. So, but these are interesting ideas, I think, on how you can probe smaller and smaller dark matter masses. Okay, and this is all I had to say about direct detection. So in the following, I have some slides on indirect dark matter detection. So maybe again, if there are any questions on this, we take them now, and okay. Otherwise.
So is there any question? People can raise hands. Seema.
Henning, I wanted to ask this earlier, but then missed the opportunity. So a quick one, that how do you decide that how deep the experiment should be? I mean, sometimes 1 kilometer, sometimes 1.5. So is there any sort of guidelines for that, or it's just like whatever is convenient technically or logistically?
Yeah, I think whatever is convenient, the deeper the better. But I think, right, it depends a bit on the size of your experiment and sort of the background rate you would expect then, yeah, and how large your how does the cosmic background rate compare with the other backgrounds you have. It's, yeah, I think generally the deeper the better, but sometimes, as I said, the radioactivity of the rock can be different, and so in that case, deeper is not always better. So it's a balance of all these considerations. Yeah.
Okay. Thank you.
Yeah, and there are a few labs around the world, as you know.
Yeah. I see no other hands, Henning, so we can move forward.
Okay, so in the last, however much time I have, I don't know, half an hour.
Yeah.
I'll talk a little bit about indirect dark matter detection. I have to say this is not, I'm not an expert in this, but yeah, I guess I know some things. And I'm just going to try and explain sort of the basics on how this works. So in indirect searches are not based on dark matter scattering, but dark matter annihilation, right? And this can still happen today as long as there is a sufficiently large dark matter density. Yeah? And so the regions that you would look to for such signals would be like the center of the galaxies, or even clusters of galaxies where this could come from. Or if we want to look a little bit more closer, then the center of the sun, you could have a sufficient density of dark matter that you could get annihilations and the decay product of these annihilations is basically what you want to see. The final states generally include photons, neutrinos, light leptons, and hadrons. So right, you have two dark matter particles annihilating into standard model particles, and these standard model particles then decay, and what you can observe is sort of the end product of those decays. So these experiments generally have good reach at large masses, because at that point it becomes more easier to distinguish a signal from other astrophysical backgrounds. And in the case where we have a decay into two photons, so we have an annihilation straight into two photons, then they would be monochromatic, and each photon energy would correspond to the mass of the dark matter particle that annihilated. And so this would be a quite striking, clean signal, because you get a nice peak rather than a spectrum. In order to compare to the constraints from direct detection that I just covered, where now we also have some mechanisms to map them onto with the collider searches. So you can only compare the constraints from neutrino telescopes in a sort of model independent way. Because in general, direct and indirect searches probe different couplings in the dark sector. Okay, so yeah, so what do we get again? So photons, pretty much everything eventually will produce a photon, and right, so if you have annihilation into hadrons, they decay at the end of the day. You may get some pi zeros, and the pi zeros will decay to two photons. So, but then you can also have internal Bremsstrahlung, which actually is quite interesting, but also final state radiation. So this all makes you photons from dark matter annihilation. Neutrinos you get in a similar way, right? From charged pion decays, you get neutrinos that you can see, and we can also get anti-nuclei, and this can be anti-protons, but also anti-deuteron or even anti-helium, and they can arise from hadronization of dark matter initiated jets. So the rates for this will be fairly small, but it's possible, it can happen. And then the kind of nice feature is that if you look at the expected signal from that, it's sort of, the dark matter makes you a bump, whereas these astrophysics backgrounds, they are typically just they're just a smooth distribution that is falling. And you will get a cutoff of the spectrum at the dark matter mass. So in that sense, it's nice, but the challenge is this figure here on the right is not to scale. So typically this dark matter is really just a small bump on a large background, and it's quite difficult to find. So I'm going to give some examples of these photon, neutrino, and anti-nuclei searches, and yeah, we'll see what the status there is. So photons are nice generally. Well, it depends a little bit where they are produced, but because they're neutral, they propagate without deflection. And sources can be dwarf galaxies, and the central region of the Milky Way, the annihilation is proportional to dark matter density squared. I guess that's true in general. But photons from internal Bremsstrahlung, fragmentation, or final state radiation, they give you a continuous spectrum up to energies that again correspond to the dark matter mass. So that's sort of a smeared out spectrum. Whereas if you are getting the direct annihilation into a pair of photons, then you could possibly observe this monochromatic line at the dark matter mass. There are different experiments that are looking at gammas in different regions of the sky. I picked out two here. One is the Fermi telescope. So that's a space telescope, and that can collect photons in the energy range between 8 kilo electron volts and up to more than 300 giga electron volts. So really rather high energetic gammas. And it consists of two components. One is the large area telescope, and the other is this gamma ray burst monitor. And the other one is HESS, which is an array of ground-based atmospheric Cherenkov telescopes. And the energy range there is quite different. It's quite a bit higher. So it goes from order 10 GeV to order 10 TeV. So it can really measure very high energetic gamma rays. And so by looking at dwarf spheroidal galaxies, they are good for these dark matter searches because apparently there's not much significant astrophysical background at gamma or X-ray frequencies. Limits have been set on dark matter annihilation cross-section. And you can see them here on this plot by final state. So the horizontal axis is again the dark matter mass. And then on the vertical axis, you have a limit on the velocity averaged annihilation cross-section. And there is into different final states. So it's very small, I'm sorry. So from top to bottom, left to right, it goes into electron-positron pairs, muon, anti-muon, tau-tau. So on the left are the leptons. And on the right, you have into UU bar, so light quarks, BP bar in the middle, and then at the bottom, WW, which only is possible once once your dark matter mass is larger than the W. And so in some cases you can exclude. So this assumes that this annihilation is only into this final state, and you see these solid black curves, they dip below this gray dashed line, so you can exclude thermal WIMPs below different masses which go up to 100 GeV in the case of BP bar, for example. But so this comes from these dwarf spheroidal galaxies, which are meant to be good for these type of measurements. But then if you look at the galactic center, there is this axis, and it's a fairly long-standing axis that Fermi has observed. It's again a good place to look for dark matter, but there are a lot of large backgrounds at almost any wavelengths. And the origins of this axis are, let's say, remain controversial. So what you see in this bottom left plot here is the data of FERMI-LAT. This is just the axis plotted, so the axis that is expected over this astrophysical background. And then you have different models fitted to this data. Among them, dark matter with, I think, it's a 43 GeV dark matter particle that's decaying to BP bar, if I remember correctly. Another sort of popular solution to this are these millisecond pulsars. They are shown here in this purple color. So you see the low end tail of the spectrum doesn't actually fit that well. But then with more statistics, it will also be interesting what is happening to this high end tail, because I think that then you cannot really describe with the dark matter signal. So yeah, to summarize, I think that there is an excess, but it's still really heavily debated as to what the origin is. Then Hess has looked at as we said, it's sensitive to higher energy ranges. And with the latest data here, which is shown in red, there isn't really any deviation from the expected limits. Again, these are limits then on the velocity averaged and dark matter annihilation cross-section. Okay, so then we can move on to neutrinos. Yeah, just like photons, they propagate undeflected, but as we all know, are much more difficult to detect. Just because they don't interact that much. And then at low energies, there are atmospheric neutrino backgrounds. But here, the sun and the center of the Earth even are promising sources for neutrinos that come from WIMP annihilation. And experiments that are looking at this are Super-K, IceCube, and Antares. And so if you look at WIMPs from that annihilate in the center of the sun, so the only neutrinos are basically in that environment. Neutrinos are the only thing that really can escape that and arrive at us sort of unmodified. Just a few words on these experiments. So IceCube is a gigaton neutrino detector in the Antarctic. And what you are looking for, again, you have these, you sort of have photomultipliers that are looking for light that is generated from neutrino interactions in the ice. That gives you Cherenkov light, and you can detect that light. And you have these the PMTs, they point in different directions, and so you can distinguish light that comes from above and from below. And it's really deep. It's 2,500 meters deep, and it's a incredibly large volume that is active, basically. Antares is a similar principle, not quite as big. It's a large area water Cherenkov detector that is in the Mediterranean Sea. And again, you have this, you look for light signals, but it's optimized for muons from high energy astrophysical neutrinos. So what do we get on this here? So these experiments, the results here we can display in the dark matter mass versus spin dependent dark matter proton cross section. So in this yellow line here, we see the limits I discussed earlier from these bubble chambers. So this is the pico limit. And then here, we see limits from IceCube, Super-K, and Antares. And you see, again, that different experiments are sensitive to different regions of the parameter space here. And then the different colors here is the annihilation into different assumed final states. So blue is BB bar, green is WW, and red is into a pair of taus. And so in this particular I guess scenario, these indirect neutrino neutrino detection experiments are quite sensitive. If you look at a spin independent projection, you see that the liquids are experiments here have a better sensitivity. They've done something. So again, these projections, they depend on the velocity distribution of the dark matter that you assume. And so recently, because Pico and IceCube have the best sensitivities for this particular observable, so the spin-dependent scattering of protons, they've done an analysis that is independent of the dark matter velocity distribution, and you can see the black curve here is their combined limit, which is well, quite a bit weaker than the limits achieved when using the standard halo model, but it's an interesting result that they get these that they still get reasonably good limits that are less model dependent, if you want. Okay, so that was neutrinos, and then what is left is charged cosmic rays. And so unlike neutrinos and photons, they they get deflected by magnetic fields, and so they really can only reach the Earth when produced within a few kiloparsec without being too modified too much or absorbed or something like that. What one looks here, just because it's easier, is so you would think that positrons or protons would be produced in equal amounts, so the electrons in the same way as positrons, or protons in the same rate as antiprotons, but it's much easier to search for the antiparticles because the background there is much smaller. And so what one searches here is for excesses in the flux of positrons, antiprotons, and even sort of anti-nuclei, like deuterons. And however, extracting dark matter properties from those spectra is much more challenging as they will be modified during the propagation, right? As is mentioned, there's magnetic fields simply in the galaxy, but then it gets much more complicated once they come close to the sun, because the sun's magnetic field reaches out quite far, but is sort of fairly unstable. So there are a lot more, conceptual and I guess experimental challenges associated with this. The best apparatus to look for this is AMS. Basically, AMS is a particle physics detector in space, and has everything you need or want. It's got tracking, it's got calorimeters, it's got particle ID, it's got a magnet, so you can really measure momentum, charge, and mass of the particles that are entering this detector. And it sits on the International Space Station and is happily collecting data. And so AMS has produced a few interesting results, and the first one is sort of this excess of the positrons. So what you look is at the number of positrons over the sum of electrons and positrons. And on the left here, you see the expectation from astrophysical background is sort of this falling line here. And it started with Pamela, these are the blue points, and then later confirmed by AMS, so that there is this steep rise. And again, the question is, could this come from dark matter annihilation into, I don't know, electron-positron pairs, or muon, anti-muon, but eventually by the time they come here, they show up as positrons. Now, with more data and better understanding, I think the excitement is certainly much more reduced now, because one of the problems was that the amount of the excess was just so much larger than what one expect from dark matter annihilation by sort of 2 orders of magnitude. And also such large rates, they were basically excluded by constraints on the annihilation cross-section from Planck, basically, which set these limits that one can see here in the figure on the middle. And I think what since then has emerged as the most likely explanation for this excess is this positron emission from pulsars that can explain this large positron contribution here. So this is what is called the source term here. So the diffuse term, and then this source term is from positrons coming from pulsars. So yeah, probably it wasn't dark matter. Then the next thing is the anti-proton spectrum. And again, AMS observed a slight increase here in the rate of anti-protons compared to the expected background. It's hardly visible in this plot here, but in this range here, there is a bit of an excess. The size of the excess is much more in line with what you would expect from dark matter annihilation. So it's not like orders of magnitude out. But as I mentioned, because these protons, they propagate through space, so the modeling of this background is that there are still questions around that in order how accurate this is, right? Because questions about the production of antiprotons, the propagation, solar modulation, and then eventually instrumental effects. And here is a paper that came out just this summer that then tries to fit this antiproton spectrum. On the left here is without the dark matter contribution, and they have 2 different fits. One is where they consider correlations between the systematic uncertainties of the AMS measurement. And you can see that in red, when you include these correlations, you get the residuals are much smaller, so that there's much less evidence for an excess in the data. But if they include a dark matter signal, they still fit some strength for it. It is just reduced compared to before. So again, I think simply an open question, but there might be some hints there, some possibilities for dark matter annihilation showing up in the anti-proton spectrum. And then finally, there is anti-nuclei, so in particular anti-deuteron and anti-helium. And in principle, they are really good signals, because unlike for positrons and antiprotons, you would really expect them to show up as a big bump over your background spectrum rather than just a small percentage-like modification, because they're typically more at the lower energy end from dark matter annihilation, whereas you only get these anti-nuclei in your astrophysical background when they have really rather large energies. The problem, though, is that this is strongly suppressed compared to antiprotons. So here you see this is the rate versus the energy per nucleon, and you can see, I don't know how well you can read the scales here, but from protons to deuteron, it falls by 6 orders of magnitude, and then another 4 orders of magnitude for anti-helium. There are different. There's been a lot of debates how calculate these fluxes, and with different assumptions. There's this darker blue band, some group derived, which is then 2 orders of magnitude larger. So there's still a lot of uncertainty, I think, in the modeling of these things. But the interesting thing is that AMS has recorded 8 candidates for anti-helium 3. And again, based on these expectations, this is a way too large rate, but it is rather exciting. And one thing that was proposed recently is that rather than prompt production of this anti-helium, is that it could happen via lambda B decays. And as is shown here on the right, this would give you a fairly large contribution compared to prompt, but in the relevant energy range that is relevant for AMS, it dominates, by, I don't know what it is, probably a factor 100 or so. And so this is one option to explain the observed rate, possibly, but again, there are a lot of things still, I think, to be better understood. But I guess what is interesting in all of these is that both in anti-protons, in positrons, and in these anti-nuclei rates, AMS has seen excesses. And they could be connected to dark matter annihilation, but I think these processes still need to be better understood. Okay, this brings me to the end of what I wanted to talk about. So here's my summary. I hope you've seen that direct dark matter detection is a very active field with many new results that are and experiments coming online. And a lot of exciting ideas being developed, in particular when looking for lighter dark matter based on quantum technologies. And yeah, so these complement established techniques for heavier WIMPs to push really down to GeV, MEV, or even KeV WIMPs. And then for indirect dark matter searches, they are, I think, still more difficult to interpret. The results from the neutrino telescopes are probably the most relevant for comparison with collider and direct detection, but there are excesses in all of these sources, right? Whether it's the gamma excess from the center of the Milky Way or the things I just talked about. And again, here on the left, looking at this dark matter proton scattering cross section, the spin dependent one, you can see that these the limits from IceCube and supercammucanted, they are really quite competitive and strong, in particular these high dark matter masses. And that's all I have to say. Thank you very much.
Thank you, Henning. So let's see, it's kind of late now here also, but let's see, this was a 2 hours marathon talk. So let's see for Seema, please.
Hi, Henning. Thanks a lot again. So I have a quick question on when you're showing about this AMS results, slide 53, I think. So although you mentioned it, that, okay, the astro, all these backgrounds have large uncertainties. So is there any further insight on like what can come from these? I mean, so previous one actually. Yeah, this is what you're talking about, right? Yeah. So it's not like an order of magnitude different, right? It's just, so is there any further insight like there can be some issues with the astrophysical backgrounds or?
Yeah, so this here, sorry, this is sort of the old story, the plot on the left, right? This is how the data came in, Pamela, then the first AMS result 2013. And then here the plot on the right is actually the same spectrum, but with the latest data. Yeah.
Okay, fine. Then got it.
Yeah, sorry.
Something remaining there. No, this one I'm familiar with, the source from and the diffuse from.
Yeah. So it's the same plot, just with more data, and you can say it eventually does turn over and you have this pulsar emission that is the likely cause.
Yeah, I misunderstood that. I thought there is something still going on in other one.
Yeah, no, unfortunately not.
Anybody else wants to ask anything? No. Okay, I don't see any hands. So thank you, Henning. It was wonderful to have you with us actually for this 2 hours pedagogical talk. And we'll look forward have you in the future, invite you to India and listen in the offline any meetings. But with that, I will thank you again, and we can close the session, and we'll meet at 9:30 tomorrow.
Thank you for the invitation, and yeah, I guess it was a bit of a tour de force, but I hope it was interesting.
Sure.
Thank you.
Yeah. Thank you. We'll meet at 9:30 tomorrow for the last day of the conference. Thank you. Bye bye.
Bye bye.
Bye. Thanks, Henning. Thanks, everyone.